How's everyone doing? You made it. Lots of folks didn't. That's okay. Generally speaking, the rule for attendance is if you are worried about your health, if you're worried about your safety, this class is not that important. Okay? We'll agree that your health is more important than one class. I prefer if you can email me ahead of time. That's usually the easiest way for me to keep track. And then when it comes to doing your attendance later, any activity like this. So today we had a lecture tutorial planned, but with probably a third of the class missing, we'll just push it till Thursday. Is that reasonable? Okay. Folks in the chat. Oh, let's not leave it there, because then everyone else can see it. All right. Cool. Should we get started? Any question before we start? Okay. What's that? Anyone seen a rocket launch? Anyone seen like a really bright blue thing going across the night sky? Yes. Yeah. Well, not always SpaceX. It's from Vandenberg. So Vandenberg is our closest Space Force base. Yes, that's a real thing. Yes, there is a good reason to do it. Yeah, SpaceX does a number of launches from the facility there, but some of the major launch providers are ULA, Boeing. There's lots of aeronautic companies. So JPL is not actually a launch facility. JPL is a research institute, so they'll build the technology that will go on. Oh yeah, speaking of JPL, this is a Dodger hat that I got for JPL night, and then on the inside has like a spaceship. Yeah, nice big flex. All right. Do you know where this is? Why is it for that? Water? Yeah. Yeah, this water here. Yeah, that's how you can tell. So this is from the Kennedy Space Center. So I got to watch the spacecraft that I work on, Maven, launch from there in 2014. That was pretty cool. If you've ever watched a rocket launch, it's incredible. These are very tall things, and it's mostly fuel. So like all of that up until this little tiny piece at the top is fuel. Well, this one probably only about 100 feet, so 10 stories of fuel. The one that we went to the moon on is called the Saturn V. And to go to the moon, that's the farthest that humans have ever been from the Earth. That is 190 feet of fuel. Something like a 19-story building, and you're strapped to the top. Yeah. So not for the faint of heart. Okay. We all did the reading, right? Okay, we all have our clickers? All right, let's get those brains started this morning. Come on, Ned. No. I was 6. Yeah. Sorry, that's telling, right? Okay. Let's see if this works. Let me read this off really quickly and just see if I have to redo the poll here. Oh yeah, it's working. Okay, so Ptolemy, we don't pronounce the P, silent P like pterodactyl, right? Okay. Ptolemy was important to the history of astronomy because he A, developed a model of the solar system that made sufficiently accurate predictions of the planetary positions. B, developed the first scientific model of the universe. C, was the first to believe in the Earth-centered universe. D, was the first to create a model of the solar system that placed the sun rather than the Earth at the center. Or E, was the first to use perfect circles to represent all of the planetary orbits. So voting is open, so you can just dial in when you're ready. I know you're all ready because you're all prepped. Okay. Interesting. Interesting. People in the room have a very different answer than people online. I don't know why that is. So the majority answer in the room is A, and the majority answer that I see in the chat is D. And I don't know if people seeing each other's votes is swaying the people in the chat. This is a reading question, so we're going to answer this question as we go through it instead of just talking about it right now. So let's talk about who Ptolemy was, and then we'll figure out which one of these is correct. And if you guys love trick questions, you know, right? Okay. Excuse me. You can't see the screen fully? Are you, sorry, which version of the screen are you seeing right now? Are you seeing the presenter view or are you seeing the slides? It starts showing at B. Okay. I don't know what's happening online. I'm sorry. It's a disaster online when you watch it back. I bet. Okay. So the Greeks, we were talking about this idea of parallax. As we move around, the background is going to stay fixed, and the stuff in the foreground is going to appear to move back and forth. That's the idea of parallax. Parallax is another word for shift. And so they said that the lack of observable parallax, the fact that they couldn't see the stars move, meant there were only two conclusions. One was that stars were too far away. That is to say, parallax existed, but you couldn't see it with the naked eye. And they thought, that's preposterous. How could that possibly be true? Because they measured the relative distance to things like Venus. They knew how far away Jupiter was compared to the Earth. They didn't know it in terms of total amounts, but they knew them in relationship to one another. So they could say like the moon was this far away, and then the sun was much, much farther that same distance, right? And so they said, well, it must be the case that the Earth does not orbit the sun. It must be the center of the universe. So they looked at this evidence and they thought that seems impossible. Okay. So did they miss something? Right? That's the major question. So this is an image of Mercury and Venus, or Mercury or Venus. I forget which one I have here. But this is what it looks like over the course of the year. As I mentioned, you can go out and you can imagine taking a photograph of the same location every day, and you'll watch certain objects in the sky will change their position day to day. So the sun is going to move north and it'll move south, and then move north and it'll move south. And if you go out when you see something like Venus, sometimes called a morning star, that's because right before sunrise, it's visible and it's very bright. So people thought it was a star. And perhaps you start watching on March 1st, very low on the horizon. And throughout the course of the year, it'll go up and it won't get past a certain height in the sky, and then it'll come back down. And it'll stay hidden for all of the time in between there, unless you wake up before dawn. Okay? So they looked at Mars and Mercury, and they said, okay, this has to be an epicycle. Remember, that was a circle in the motion of these planets on the night sky. They said that these epicycles were linked to the sun. The rest of the epicycles were not linked to the sun. They were just around the planet's orbit. Okay? But this might have been early indications that something was weird. Because now you have to treat two different objects separately. You had to treat the objects that are close to the sun, these Mercury and Venus. You had to treat them differently than Mars, Jupiter, and Saturn. Right? This is another example of retrograde motion. You can see the path. It's kind of hard to see on here, but you start up here, you head this way. This is January, February, and then it goes backwards like this. Is this retrograde motion of Mercury or Venus? The answer is no, and I can tell you why. Here you see this object, this planet, starts March 1st, goes and makes a loop, and then comes back down. And it does it rather quickly, in like less than a year, right? Whereas look at how far this is moving on the night sky. So this moves from here to here in about a month. Now you don't know how big this is, but you can see that there's constellations and whatnot here. So this thing doesn't even move very far in a single constellation in a month. So this is the idea of objects moving quicker or slower in the night sky relative to the background objects. So because this appears to take a long time, right? So this is the beginning of January 2016, and this is October, right? But it's only passed out, it's only gone through a small section of the sky. Then you would say this is a slower object. So likely to be something like Mars or Jupiter. I think this one's Mars. Okay. So the big question is, why did the ancient Greeks and everyone else until about 500 years ago, why did they reject the real reason for planetary motion, the real explanation? And mostly it's this inability to observe the shifting of the stars, right? That's the primary reason. Okay, there's the image, right? As you go around, you expect to see this thing. You expect to see nearby stars projected onto the distant stars, and you expect this little purple star to move. Does this process make sense? This is the picture of parallax. Anyone not getting parallax? So now I'm going to ask you a philosophical question based on. Oops, I left this multiple choice question open for 8 minutes. Okay, so let's try this one now. Was Ptolemy's approach following the correct scientific method? Yes or no? Okay, we got some A's online. We got some B's. This looks much more split, which is great. Click in if you want to click in. But this is an ideal question because in the classroom, it's about 19 and 19, which is amazing. So turn to a friend, ask them, or turn to whoever, doesn't have to be a friend. Just ask them what they got. If it's the same thing that you got, find someone else. and then try to convince them why your answer is right. But I mean, listen to them, right? Obviously you're right, but listen to what they have to say, right?
Yeah.
That's fair. That it? Everyone got it? Should we try again? Try again. All right. Still even as I watch it come in. 18 votes in. Revote if you want. Still dead even. 12-12. Yeah. Oh, okay. That's okay. That's okay. The quality of the answer here only affects what I think you understand. It doesn't affect how your grade ends up. And you can answer wrong in the clicker. I just want you to answer. That make sense? Okay. And we'll talk about the answers in here, and then you'll see them probably in the homework. Okay, so 14 versus 11. Is that anyone in the classroom wants to click in? Anyone want to explain their? Anyone feel brave? Yeah.
I said that he was approaching the correct scientific method because to him, and back then they had no way to observe the parallax. They had no telescope or anything like that, so they couldn't really, other than them just looking at it with their eye, they had no way to see if it was actually moving. So to him, that was all the observations he had.
Right. Right. So let's go back one step here, right? Let's think about what they were presented with. So they had, let's see. They had this conundrum, right? They said, if we are moving, then we should expect to see parallax. So they made a prediction. Then they took observations and they didn't find it in their observation. Right? So they assumed that this first part was wrong. They made a testable prediction, they tested it, and they came to the wrong conclusion. Does that mean science is broken? No. This is why reading scientific headlines is very infuriating. Because for the most part, scientists are talking to each other, right? They're saying, oh, I found this thing. And then you tell the whole world, and it's like, well, it's really a conversation. Right? I found this thing, we think it is right, but it could be wrong. And then anyone listening says, oh, you said this, and then you changed your mind, and then it's okay to change your mind. You get new information, you're supposed to change your mind, right? That's part of the process of learning. Okay, so this was part of the scientific process. They just got it wrong. That's perfectly fine.
I guess you revise that one. They would be losing a movement finding perspective on it.
Right, right. And you'll see, we'll talk about a version of gravity, and that version of gravity worked for hundreds of years until observations didn't support it anymore, right? And you have to revise it. Okay, so let's move ahead. Let's talk about something called the Copernican revolution. So this is the idea of a geocentric, that is to say, how do we center the model on the Earth, us, versus heliocentric, which would be on the right-hand side. And you'll notice this is a really cool diagram. All they did was they switched the locations of Sol. So Sol is the yellow one here, and it's in the center here. And here's Tellurus, or the Earth, and that was at the center here, and now it's over here. Okay. But of course, these two models both use circles, perfect circles. And I'm like, let's say it's 500 years ago. I don't know, they look the same to me, observably, right? Ptolemy was famous for putting those circles on circles to explain retrograde motion, and he did a really good job. He got the retrogrades correct according to the eyeball, right? Okay. So we're going to talk about how the sky change. Wait. Oh yeah, we're going to talk about how the sky changes when we move around the Earth. That's the concept of parallax. And we're going to say, why did scientists challenge this model that had been around for thousands of years? Not thousands, 1,500 years. So Ptolemy, remember, is in ancient Greece, and the heliocentric model is not developed until the 1400s. So what changed? Right? Will you do another clicker question here, or we just skip it? You guys are ready. You did all the reading, so you can definitely do this one, right? So you know who Copernicus is because you did the reading, right? So let's try this one out. Why didn't Copernicus's model accurately predict the position of planets? So Copernicus was an early proponent of the heliocentric model. Did he A, have the order of the planets wrong? B, he had the distance to each of the planets slightly off? Did he C, still have the Earth at the center of the solar system? D, he used perfect circles for each of the orbits of the planets? Or E, it was accurate because he had a model where the sun was at the center? Click in when you're ready. Very few people liked A, B. Most of the answers are grouped around here. Interesting. Interesting. Anyone else want to click in? Okay. Most popular answer is D right now. Doesn't mean it's the most correct answer. Just saying it's the most popular answer. Okay, so let's find out what happened. So here's Copernicus. That's not exactly what he looks like because that's made of bronze. You get the idea. He proposed a heliocentric model. He was an astronomer. He would take very detailed observations of the motion of objects in the night sky. And he used circular orbits to determine the layout of the solar system. Okay. But it wasn't better. So I showed you that picture that had the two different models, the geocentric and the heliocentric model. If you use perfect circles with the heliocentric model, it's not better than the geocentric model with little circles on circles that Ptolemy devised 1,500 years earlier. Right? Okay. So then you have this bro. He's very cool. His name's Tycho Brahe. Late 1500s, the greatest naked eye astronomer of all time. Like super precise measurements. This is something that measures, like it's this big. It's like a room size object to measure locations of stars on the night sky as they cross the meridian. Like the perfect precision. Not great, but very good. So you got super detailed measurements. Fun story about Tycho Brahe. Uh, he also had his nose taken off. He had if you look at any of the pictures, like paintings of him in the later part of his life, he had like a bronze nose. And theoretically, he died from uh, urinary tract poisoning because he believed it was impolite to get up to go pee in the middle of this very long dinner. And he died. Astronomers, scientists, weird people. End of Isaac Newton's life, also very weird. He would stick like probes in his eye in order to understand the optics. And he went on to be, you guys know what counterfeiting money is? Yeah, so he would hang counterfeiters in the streets of London. So like, taught us about like gravity and calculus and also murdered counterfeiters. I don't know. Very weird. What? No, no. I mean, it's very debatable on the conditions that they died, right? Because they didn't have modern autopsy tools, but it wasn't mercury. Mercury would like kill you, right? It'd be immediate. Okay. So Tycho made this Tychonic model of the solar system. This is a slight adaptation to the Copernican model. You don't have to memorize all these names. I know what the names are. You don't have to. What I want you to think about is the slight improvements to the model that are being made. Okay. So he did this weird thing. He said the sun orbits the Earth, but the rest of the planets orbit the sun. Okay. A little silly in retrospect. He had a student named Johannes Kepler, and Kepler tried to match these observations with circular orbits. He was using the Copernican theory. He said, I tried to do this with circular orbits, and it's just not working. Okay. So eventually he tried ellipses. So what is an ellipse? An ellipse is like if you had a circle and an elephant sat on it. So just squish the circle like that. Okay? And if you use a squished circle, it works. So Kepler was like really excited. And the reason why they found this out, and this is a great story for anyone who goes to grad school, he wanted to keep all of the best data. Tycho Brahe was like, man, I'm getting like really good results with Venus, and I'm getting super good results with Jupiter and Saturn. But Mars is giving me a headache. I can't make Mars work. So he's like, all right, Kepler, take this crap data that I have on Mars and try to make that work in your stupid little model. And it turns out that Mars is one of the more eccentric planets. That's not just a description of like something being weird. What it means is like not being perfectly circular, but more squished. So Mars actually gets significantly closer and farther from the sun throughout its orbit. And because of that, it was easier to fit these ellipses to it. So that's a fun little coincidence in nature. Tycho Brahe tried to ruin his life by giving him bad data. He turns around and says, oh, I actually have the right answer and you don't. Don't read that. That's hard. Okay. So here's the ellipse. On the top there's the circle. When something has east. Hello. What happened? Wow, it really did not like me talking shit on Tycho Brahe. It like literally just closed PowerPoint. Nothing was even happening. Yeah, I know it. Here's what Microsoft has to say to me. Oh, really? All right. Hopefully that comes back. Awkward. I don't understand. Now PowerPoint can't be opened? Someone in the chat said he's haunting the class. It's pretty good. It's actually pretty fire. Oh, you know what I bet happened? CSUSB loves to update your apps regardless of when you want them to. Oh, I don't want that class. That's the wrong class. That's Mercury. Okay, let's open this one. I'm sorry, folks. Deeply unprofessional computer. What's that? Yeah, that's exactly why. That's 100% why. Couldn't possibly be the computer. There we go. Enable content. Here's an ellipse. All right, now we're cooking. Can everyone still see it online? Thanks. Okay. So a circle is just a special type of ellipse. Just like a rectangle and a square, you know, they're friends. So square is a special type of rectangle where all the sides are the same. And a circle is a special type of ellipse where this measurement of the squishness is 0. So the squishness is called the eccentricity. Eccentricity, we sometimes use the letter E. So that number can go between 0 and 1. So if the eccentricity is 0, then the orbit is a circle. If it's 1, then it's something very different that we'll show later. So here's some examples. That's like a moderately squished circle. That's an E of 0.7 or 70% squish. Here's a highly eccentric ellipse, and this is 0.9 or 90% squished, right? So it's just a measurement of how squished it is, 0 to 1. Think of it as 0% or 100%, right? Is that process okay? We like this word? Okay. So Copernicus said all orbits are like this, circles. Circle, 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 and he got it wrong. Kepler came along and said, okay, we're going to use slightly squished ones, and he got it right. Okay. Now this is a fun one. Which of these two objects is the Earth's orbit? One of these is a perfect circle, and one of these is Earth's orbit. Okay, is it this one? Is this Earth's orbit? Raise your hand for Earth's orbit. All right. This one? Earth's orbit? I don't want to answer questions? Okay. All right, we got almost everyone. So that's perfect circle. And that's Earth's orbit. Okay, so you can see how for the most part, perfect circles work great. I mean, that's just a tiny, tiny deviation, right? That's like a almost 2% deviation. So that's imperceptible to the eye, right? You can barely notice it on me. Okay. And there was another thing that happened in the 1500s. Does anyone else know what happened in the 1500s? What? Say that one more time. Okay, yeah, that might be true, but that is not relevant to heliocentric model. Yeah, Galileo. Yeah, there's something happened before Galileo. Something very important that talks about the relationship between science and technology. Invention of the telescope. Okay, so in the 1500s, they developed this cool new tube for looking at enemy ships. So you can shoot them before they shoot you. That was the point, right? A lot of warfare was on the ocean. And you see a ship coming towards you, you got to know if you're about to start blasting, right? So they built a tube and they put glass on both ends. And they're like, look, I can make small ship big. And they're like, damn, that's smart. Blast them, right? Okay. So then there's this dude, Galileo. He saw some stuff, right? Which of these things was not observed by Galileo? Was it the 4 moons orbiting Jupiter? B, stellar parallax? C, mountains and valleys on the moon? Or D, phases of Venus? All right, this one I guess didn't trick as many people as I thought. All right. Most people are coming out with stellar parallax, and we'll see that that's correct. Okay, so let's talk about what Galileo did do, and we'll talk about the implications for the observations. Okay, that's him. Cool name, basically the same twice. Galileo Galilei. That's not a typo. So he found this telescope. So the Dutch invented this telescope. People know why the Dutch invented the telescope. We just talked about it. But you know why the Dutch invented it? What? Yeah. So if you've ever heard of the Dutch trading company, you ever wondered why all carrots are orange? All carrots are orange because the Dutch national colors are orange. And with their enormous colonial empire, in order to celebrate their king, they said, okay, we're only going to be sending you orange carrots. They popularized the orange carrot, even though if you go and you find carrots in the wild, they will be like white or purple or orange, right? But this became very popular. Okay, sorry. I just know lots of facts. Here's the Dutch. They're looking at people that they want to like take the ship of. Like the French, the Spanish, and the English. And then Galileo, he's Italian. He's like, yo, but like, what if I look up? And he does. And he just makes really cool drawings, right? So this is a really cool time in the world history when people just pay you to do cool stuff. And like, whatever, you just chill. And so he would just like do stuff and he had sponsors. And there's a rich family called the Medicis. They just paid him, like, look at the sky. Now, did he write horoscopes for them? Yes. But we're going to ignore that part of history, okay? So he starts making these really detailed drawings. And in particular, he starts looking at some stuff that, like, I don't know, thought was pretty cool. And for context, let's recall that if you've ever, say, looked at the night sky, you've seen the moon. It looks beautiful. It looks really bright. It looks like a perfect circle, right? You look at the sun. It's bright. You shouldn't look right at it. It's bad for your eyes. It looks like a perfect circle, right? We talked about these orbits. They all seem circular. So Ptolemy put circles on circles, right? It seemed like the natural shape here was circular. And these are the heavens, right? These are the places where gods reside and our fates are decided. So they assumed there would be no imperfections of any kind, right? The moon wouldn't have any imperfections. It's not an object, it's heaven, right? Similarly with the sun. The sun is not something to be understood. It's the sun, thing that gives life to everything on earth, right? Okay. So with this in mind, I need you to think about how it would have been to be in the 1500s and for the first time to see the surface of the moon. To see it, right? You, for your whole life, have not seen the moon. Just been up there. If you like, you're like, oh, there's some fun shapes in it, right? Kind of fun, like, orby thing. But you've never seen the surface. Okay. And then, interestingly enough, one of the first things he looks at is Venus, right? He looks at that morning star, and he sees something very unusual. He sees phases of Venus. Now, this is going to require us to break down why, for example, the moon has phases that we see. So we're very close to half moon. And we have to understand that in order to understand what he was looking at here, right? And I'm going to show you the phases of Venus as we will see. But let me just break down how this works. So here's the Earth, okay? This is the geocentric model because Earth's at the center. Sun's going around us, right? And here's Mercury. That's the third one away from the moon. The second one away from the Earth. So it's here, and it has to do these little circles. This in Ptolemy's model, right? So does Mars. Mars has to do these little circles. They did know that the sun created light, right? That was obvious to them. But now they had a test for how shadows are created. Okay, so what do I mean by that? So currently you see my hand. Okay, I'm going to try and also get it for those folks here, right? So you see my hand here, and it's lit on this side. Okay. So what phase is my hand? We would call this full of light. If I look from it from my perspective, I only get one half, the front half, illuminated. So I call that half full or half empty, whatever you want to call it. Okay? And if I stand behind it, I don't see it illuminated at all. And that's called the new moon. Okay? So let's do that again. Now I'm not going to stand in the way because I need to be able to show you. So this is the new moon. I'm still looking at you. You're the sun. My hand, oops, let's use this hand, goes to here. Now it's a half. I'm looking at it. It's illuminated on this side. You're the sun, right? And then behind me, it's full. So it's the location of the moon relative to me that illuminates the phases, right? Okay, so that's the Earth, right? And the moon's going around it, and the sun's over there. And as it goes around, it shows us phases. Right? Okay. So if Mercury and Venus, right, are going around in these circles, then we might expect them to have phases, sure. But we wouldn't expect Mars to have phases, right? Let me show you an example. Oops, there you go. Here is the Ptolemaic view of Venus. Okay? Going around in these little circles. It's in between sun and us. So it goes on these little circles, and based on how it's illuminated, it's either new, meaning it's right here, or it's over here, and I can see a little crescent, right? But it can't get behind me because it's not orbiting me, right? It's going on little circles, like this, right? Let's go back one picture. This is the image, right? We see it going on these little fast circles. Mercury goes fast, right? So we see these do these little circles, right? And for some reason, these two are linked to the sun. We never see Mercury over here. Only see it low in the horizon. We see it make these little circles. So that means it can only go from here to here, to here to here. And so I should only see it new or in crescent, right? Where just the edge of it is illuminated. Okay. As opposed to Copernicus, who said, no, you should be able to see all of them. They go around the sun, you should be able to see it full when it's on the opposite side. And then you should be able to see, don't memorize these if you don't want to, but like quarter, like half on. It's over there. See half of it full. It can't get behind me, right? So I don't see it full that way. I see it full on the other side of the sun, right? Okay, so here's a test. And with the telescope, we can see it for the first time. You couldn't see this by your eyes. You had to use a telescope in order to be able to check which one of these two predictions was true. And you know which one is true, right? Okay, no one's bored by that. All right. So interestingly enough, before the invention of the telescope, you couldn't see the difference between these two. You could just tell how bright it was. That's all you could tell. And the weird thing is Venus always looks the same bright. They're like, huh, that's weird. So let me show you some pictures. These are to scale. These are real images. Okay. So that's 2004. That's European Convention of Numbers. That's February. And this is June. Okay. So what two things do you notice here? Gets darker? Yeah, so like here it looks more illuminated than here, right? Good. One, and yeah, you can see the whole ring. Yeah, that's pretty cool. But that's not the most striking thing here. Gets bigger. So we have this issue that it was the same brightness the whole time. But when it's full, it's farthest away from us. And when it's closest to us, it's only kind of illuminating. So we get a much smaller amount. But that number for Venus just happens to be about the same amount. So it gets farther away, but it gets a lot less bright. Right? So these are real images of Venus. We'll see many more then as we get into the rest of the planet. Okay? And so, for example, if it gets full like this or gets, a quarter, then it must be the case that this object goes around the sun. It's not in between us and the sun going on little circles, right? This is the first piece of definitive proof, right? If we go back here, here's the prediction. We should see from this phase to here, right? That's what this branch is, going from gibbous to crescent. Gibbous, there's like half, I think it's like right there. And then there's crescent, nice, beautiful crescents, right? But it gets big. Okay, first piece of evidence. Okay, second piece of evidence are the moons of Jupiter. So he starts looking at Jupiter. He's like, whoa, that's sick. And he starts noticing that these stars appear to be orbiting. And he just goes out there every night, looks at where these stars are relative to each other. I mean, this is a graph paper, right? This isn't like marked down with coordinates. He literally just saying, this is his real drawings. He's like, okay, 1, 2, okay, 2 on this side, 1 on this side, okay, 3 on this side, right? He doesn't know anything about them. He doesn't have a mental model constructed of what they are. He's just drawing. Drawing. And he's like, that's really weird. I don't know what these are. Sometimes he gets really lucky. He gets 4, right? Sometimes only 2. I don't know what the heck's happening. These stars keep appearing and disappearing. Okay. What are they? No, it's okay. It's right up there. Okay, we're all paying attention. So he showed that these objects, in fact, do not orbit the Earth. So it could be okay if things didn't orbit us, because he could demonstrate that this was true in another circumstance, right? Come on. Okay. And here's the moon. Okay, that's a drawing he made. He saw mountains and valleys on the moon. He saw sunspots on the sun. So that idea of these perfect circles, that was being destroyed, right? It was like, oh, no. You know how we have like these tall mountains that we can climb up? I mean, it's Italy, right? So it's all mountains, beautiful countryside. He's like, that's what this is. And he could see on the surface, right, these pock marks, these holes, saw these like large plains, right? So he was using somewhat more of a philosophical argument here, right? This is itself not quite enough to put one of those theories to bed, but when you add them all together, they're quite convincing. So the idea that everything is perfect circles, which is the primary basis of the geocentric model, once you remove that as being necessary for your model, then why does the Earth have to be so special, right? because things aren't perfect circles. So let's use the ellipses that Kepler has, right? No reason to use circles anymore because not everything that's in the heavens needs to be circular. And here's the sun. Don't look at the sun, please. Hold on now. Oh my God, don't give me any updates. All right. All right, so that's his drawing. The top, pretty good drawing. I don't draw it. And that's the sun. You can stare at it. And how did he look at the sun? Yeah, it's pretty tricky. So what you have to do is you have to project the sun, because remember what a telescope does is that it collects light and it magnifies it. So imagine, if you will, collecting all the sun's light and magnifying it to your eyeball. That would melt your eyeball. So what you could do instead is you could use those lenses, and you could use a really small pinhole and project the sun onto the wall. And you could magnify it with a lens. So where you might get a little dot that, you're like, oh, that's fine, it's not very beautiful. You use a lens, it becomes large, and now you can sketch it. Right? We have one of the, yeah.
It's like how the eclipse was happening, you look at shadows, you see there's a chunk in the scene of sunlight and all shadows.
Yeah. So that's a really fun example, right? So that's like how the shadows move around like the edge of a leaf. But I actually have a tool. I'll steal this for Thursday. It's a solar telescope, but it's like a portable one, and it can project the sun onto a piece of paper. And so we'll be able to see like these with just one lens. It's very cool. I'll show you. Very fun. Okay. So this is like mounting evidence that the sun is the center of the universe in their perspective. They don't know anything about other solar systems. They don't know about galaxies, right? Telescopes just been invented. Everything in the night sky is a star, and they're too far away to even be considered. Okay. And of course, in this class, we won't talk about the edge of the universe. Okay. Okay, so not everyone loved it though. Bummer. He was deeply Catholic himself. He wasn't trying to like shake shit up, but they thought of it as like they thought he was trying to like break down the Catholic Church, and he was placed on house arrest until his death in 1642. They finally took his book out of the index of banned books in 1824, and then just 2 years after I was born, they were like, "You did nothing wrong." So sometimes the process is slow, right? Particularly if people care about the outcome, right? If it affects your world. So you can run into conversations with people where they very deeply believe something that's part of their identity. And it doesn't matter what you say, they're going to believe that. Nothing wrong with that. But just hopefully they don't put you on house arrest. Cool. Okay. So what have we learned? Let's see. What did I say we learned? We started with Ptolemy, geocentric model. That worked really good, right? Because we only had our naked eye to compare. Copernicus had a heliocentric model, but since he used perfect circles, it wasn't better, right? He was not the first person to do this, right? 2,000 years ago, and I mentioned this in the ancient astronomy section, people had models for a heliocentric system like 2,000 years ago, and they threw them out because they weren't very good. This was better. Ptolemy's was better because it had little circles on circles. Okay. And then Kepler was like, oh, well, just throw out the circles on circles and use ellipses. Who knew shape that was invented? Okay. And this led to basically all of modern physics, the way that we think about it today, because you suddenly get people like Newton who are asking questions like, why do things, right? Galileo had done that too, trying to formalize how things move. But Newton comes along and says stuff like, what make things move, right? Okay, so they all created models, tested them to the best of their data. And as more data comes out, and again, we have this interplay between technology and science. So as the technology gets better, You have new scientific discoveries that then make better technology that may invalidate some parts of the earlier science, but also may make it better. Right? Okay. And then Galileo basically put to bed that whole idea of the heliocentric model. One of the coolest, or sorry, the geocentric model. One of the coolest things I think he did, he wrote a book, and then he said, okay, I'm going to send you a telescope, and you can look for yourself, right? So there's that idea of reproducibility. So don't take me at my word, right? I drew these really cool drawings of the moon, but now you look at the moon, and you see that it's not a perfect body, that it has mountains on it, just like I described, right? Or go look at Jupiter. Here's where you'll find these objects, right? All right. Okay. This is a great drawing as well. This is the phases of Venus and the scale. That's Venus, the symbol for Venus, right? So heliocentric describes how they move, but not why. And again, this is not a philosophical, like who set the planets in motion, but we're going to try to describe in what process do they move. So this is still a descriptive model. It doesn't describe, what the process for moving these objects are. This is something that people were greatly debating in the 1500s, 1600s, and they were talking about these things. So we saw these bright disturbances in the night sky, and Tycho could show that they were farther than the moon using that shift that we talked about earlier. Okay, so they knew that they're not like in the atmosphere. They must be far from us. Okay, so they thought, well, they must be moving in straight lines, just shooting through the solar system and then never to return again. Right? And that's until this thing called Halley's Comet in 1705 uses physics to predict that this really bright object is going to happen again. And it's going to happen when he's not alive. Right? So that's a testable prediction using this type of new model of how we understand the universe. Okay. So the two things that we want to talk about is how do we quantitatively describe the motion? So we're not going to do I'm not going to have you solve the Newton's laws. That's not what we're doing. But I do want you to understand some of the words that we're going to use. So for example, why does an object fall and how do we describe that? And I want to make sure that we don't use the same words for two different types of actions. Okay. So let's say we're describing the motion of this rocket in space. We want to use the right words for the right types of motion. Position, where I am. Different position. Okay. But camera goes position. Okay. Time. Then we have this one. Speed. What does it mean, speed? How fast is moving? Okay, so I use speed and speed. Speed is fast, right? Fast or slow? Is there another way that I can conceptualize that?
It would be distance covered, amount of time distance covered.
Distance covered in an amount of time. So if I go from here, one position to a new position, and it took like 15 seconds, that would be a measurement of my speed or, right? How fast I was. And then if I do it like that, right? Okay, that's speed. Okay, so these things are related to one another. We'll talk about a couple more things like the idea of accelerations, and that'll be related to these as well. Acceleration would be like what you feel in a car. If someone slams on the brakes and that changes your speed quite rapidly. That's a version of acceleration. Or if you're waiting at the light, you've been waiting for a really long time, you're getting really annoyed because you want to go, and then you slam on the gas and you start going very quickly. That's changing your speed very rapidly. That's a form of acceleration. There's also a form of acceleration where you don't change how fast you're going, but you do change which direction you go. So if, for example, you're driving up a banked curve, you're turning the car, you're staying at 60 miles an hour, but you're turning, that's also something we call acceleration. And I'll show you all these examples. Okay, let's skip that question because I just said it. I'm going to only introduce 2 of the 3 laws of motion because I don't think you need to know the second one. It's got math in it. It's going to make you go to sleep. You won't love it. But you need to know 2 to understand how things work in space. 1, an object moves at constant velocity. You can use the word speed here, but I'm gonna imagine the word velocity, and we're gonna show how they're slightly different. If there's no net force acting upon it. Okay, so that's not very helpful because that introduced a lot of different words. We don't know what a force is yet. We don't know what velocity is yet. We haven't defined them. But this is the first law proposed by Galileo and then recodified by Newton. And what they're essentially trying to say is that an object at rest stays at rest. Okay. So my water is going to stay there until I take that. Okay. But they did this weird thing is they said, imagine something is moving and there's nothing slowing it down. Then it's just going to keep going forever. So this is a weird hypothetical because there's no place on Earth like this. Everything always comes to a rest, right? So whether that's due to friction with the ground, whether that's due to air resistance, whether that's due to like something in the fluid, in water, like coming into contact with the water and slowing it down, everything comes to a rest. So that's kind of a weird idea to even say, right? So this basically says, I take this object and I throw it, and now let's imagine that we're in space, throw it in space, there's no air, just gonna keep going forever. Okay? And it'll go in a straight line. That's really important. Okay. So this is gonna lead us to the definition of velocity. Velocity is just the combination of direction and speed. So if I'm going 40 miles an hour in that direction, that's what I need in order to describe velocity. Okay, there's a different word for speed, a little more newtons. Okay, and we're going to talk about net forces in a second. Acceleration is a change in that thing. So it can be a change in speed. Why does it say speed? That's so weird. That's supposed to be the word speed. It can be a change in speed or it can be a change in direction. And those are both versions of velocity, right? So I can slow down and speed up, or I can go around a circle. Or I can do both. Those are all fine. Those are all accelerations, okay? Is that fair for everyone? What you will experience on a day-to-day basis is an acceleration. Your phone, I don't know where my phone is. Okay. Your phone has an accelerometer in it. It measures the acceleration, so it can tell which direction it's oriented. So you ever wondered like how it knows to like look on when you turn it up? It's because it knows that it changed its position. So if you, for example, have it on your car and you're driving and you start speeding up, it sometimes will just show its screen. That's the accelerator thinking that you're picking it up and you want to look at it. So. Okay. Yeah, so if you have lab tonight, that's canceled because of a fire stuff. Sorry. If you didn't get that email already from Riley. That's our grader, by the way. That's Lucian. So hi, Lucian. Okay. Okay, so that's the first law. Objects in motion remain in motion. So if there's nothing to slow you down, you won't slow down. If there's nothing to change your direction, you won't change your direction. Is that fair? Okay. This one is the more fun one, and the reason why we had a rocket at the beginning Okay, this one says for every action, there's an equal and opposite reaction. And this one is a little tricky, but I promise it's true. Okay? So in the context of space, Kepler argued that if the moon pulls on the Earth, then the Earth should pull on the moon. But we can demonstrate that here with more tangible things. If I do this, right? I'm pressing down on the table, and the table's pressing up on me. Okay. Who's homework should I use? Wait, hold on. Let's do that. All right. Can I have a volunteer? Yeah. Yeah, I need to hold this. Okay, do you think I'll be able to stand on this when he holds it? You don't think so? Wow, everyone said that really quickly. All right, ready? I don't want to go through. I don't want to break it. So if I tried to, it would probably come out of its hand, right? Or it would rip, right? That's the more likely outcome. I don't want to ruin it. So this object here cannot give me as much force as I give it, and so it will fail. Right?
What if it's different material?
Well, try this now, right? So let's say I have this object, and instead of pressing through it with my hand, now I'm not going to support it. Okay? It's fine. Right? It's actually fine. But if I had him hold this, what would happen? It would tear. Right? Because it would give as much force as possible until it broke. That's more fun, right? That wakes some people up. Okay. So this is actually what we use in order to get off the Earth. Equal and opposite reactions. So let's imagine it's a great drawing, right? Premium drawing skills, definitely Galileo at home. So I'm on a trolley, got 4 wheels, even though you can only see 2, and I start throwing bricks. Every brick that I throw, I move in the other direction. And let's say I'm super strong, and they're like big shot putts, and I chuck them, right? Then I go faster the other direction. Okay? And this is all in my imaginary world because I don't need any friction in that life. Okay? Just coasting in space. And I can breathe in space, obviously. Okay. So this is how we get off the Earth. We push stuff out very fast, and then it pushes us. And that's a rocket. Okay? So there's a space shuttle right there. You got your solid boosters on the right and left for both sides. And you just get some gas, just push it out explosively, and it pushes you up. So you're just basically on the end of a very controlled explosion. Right? Cool. So you push explosion out the end. Cool. You go up. Awesome. Let's see what else I can say. There's an action, down, reaction, space. That cool? Okay. So how do you, now we have to talk about how things fall. So everything falls at the same rate. You may not believe this. That's okay. I can give you some examples of when this is not true. So all falling objects accelerate at the same rate. Now let's remember what that means. So acceleration is not the speed, but it's the rate of change of the speed. So what I mean by that is how quickly do things start moving? So if, for example, I drop, let's think about things I can drop here. All right. All right. If I drop these 2 things at the same time, which one will hit the table first? The eraser. Everyone agree?
The way, right?
Hold on. Let's not get ahead of ourselves. Okay. All right. So this one, so that's a lot. Right? Falling objects, they didn't accelerate at the same speed. This didn't get up to the same speed. This got up to the speed necessary to hit the ground slower than this did. This moved faster, right? That's our expectation. Well, again, this is only true in our imaginary world with no air resistance. So now let's try something else. If I hold it like this, now which one is going to go hit the ground first? Same time? Oh, pretty close. This one decided to curve, right? Anywhere that we know that there's no air resistance? Yeah. Well, we need gravity. What? Sure, yeah. Create a vacuum, could drop things. That's awesome. It's very inventive and probably cheaper than what I want to do. Anywhere else? The moon. Yeah. So if we go to the moon, we can do it there, right? Okay. So let's see if we have that available. So on Earth, we have something called G, which is a measure of the acceleration. And I know that we use freedom units in life, but here, just bear with me. It's about 10 meters per second squared. What that means, for every second of time that something is falling, it speeds up by about 10 meters per second. So in the first 10 meters, or sorry, in the first second, it speeds up to about 10 meters per second. In the second, it speeds up to about 20 meters per second, right? Pretty straightforward. It gets more complicated after that, but I'm just showing the first 2 seconds. And all objects are supposed to do this. Okay, so I gave you this already. I said, what about a hammer and a feather? And I said, let's go to the moon and do it. This is the only reason we went to the moon, right? Okay, so like I said, it was all broadcast live. And the cool thing about the moon, you'll learn it's small, smaller than the Earth. So you don't quite know this yet, but that means that it pulls things less. So when they move around on the moon, they're going to do like weird things like this, because it like takes them. I just fall right down, right? Because I'm the Earth. And you'll notice as it goes here, they'll drop stuff. It'll drop slowly, then slower than the stuff that I drop. Okay. And this is a very famous experiment. In the right hand, he has a hammer. In the left hand, he has an eagle feather. This thing here is an eagle feather because the name of the landing module was called the Eagle. That's why they say the Eagle has landed. It landed on the moon. So, you know, Americans, we love our eagles. Okay, so they're going to drop them. And the expectation is that they should fall, the hammer should fall first, right? Is that true? Okay, this is another example of how we know that they didn't fake the moon landing. Because if the craziest thing happened, if these both fall at the same time, that would mean that the whole place that they filmed this would have to be completely free of air, right? And that's impossible. No one could ever do that, right? Okay, let's find out.
Tim, we copied both solar wind and penetrometer drum in the ETB.
Yeah, I haven't put the solar wind in yet, but I will shortly.
Another bouncing.
Hold on, watch this.
Okay.
A good picture there.
Beautiful picture, Dave.
And you got the eagle feather in the other.
Well, in my left hand, I have a feather. My right hand, a hammer. I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Mr. Galileo was correct in his findings.
Okay, do we want to watch that again? Okay, so this one was not the Falcon. The Eagle would be 11, Apollo 11. So I don't know what one, oh, this is 15. But here we go, let's go back. Let's watch it again. Exactly at the edge.
And so we thought we'd try it here for you.
Oh, come on.
The feather happens to be appropriately a falcon feather
Right here.
for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Mr. Galileo was correct in his findings.
Okay, so that's pretty cool. I mean, Galileo was what, 400 years ago? And imagined a world in which there was no air resistance and made predictions about what type of motion should exist. And sure enough, they were right. Okay. This is a great one. So remember that we want to contextualize everything that we learn. You guys know Calvin and Hobbes? Okay. So how do they know the load limit on bridges, Dad? Well, they just drive bigger and bigger trucks over the bridge until it breaks. Then Then they weigh the last truck and rebuild the bridge. And of course, the answer is if you don't know, just say so. That's perfectly okay. So that's not how they do it at all. But this is a great idea of not all sources of knowledge have the same level of accuracy. Okay. All right. If class is canceled on Thursday, I will let you know. But if you can't make it, or if there's more fire, and another one broke out today.
Another one?
Yeah. So let me know how everything's going. I'll assign the homework. If you can't turn it in. Questions, comments, concerns? Okay, if you need your homework, it's up here. Oh, perfect. Okay, thank you. Yeah, sorry, they're on the very back.
That's one of the homework from there.
Oh, thank you.
Thank you.
Yeah.
So my partner at the tutorial, or if not, can I turn it in Thursday?
Yeah. You have to, right?
Yeah.
Yeah.
And then if I don't get back to him because he hasn't responded to me, then I'll just do my own and just turn it in.
No, it's okay. I mean, Leslie plans not to take the class. I mean, they're not super time sensitive.
Okay, yeah.
Yeah.
Okay, I'll let you know then.
Okay,
All right,
cool.
thank you, I appreciate it.
No, I didn't even need to read all of them. You said you weren't gonna. Yeah, that's why.
Thank you.
I got in a lot of stuff, they don't say you want to have her do a letter for me. You said everything gets turned in Thursday.
Yeah, but I allowed, remember I said some people couldn't turn it in, they could be.
Yes, and then I said, can we have them turn it on later?
If you say, can you change the due date? I'm not gonna change the due date. Okay, it's not clear. It wasn't clear what you meant by that. So yeah, so if you want to come, you can come at the beginning of class. That's fine.
I have classical, that's why I came at the end.
Yeah, but it's also, you don't have to come at the end at all. I mean, I can bring these back.
I just. Sorry, I was.
No, yeah, it's crazy, right?
I'm just, participation. I'll probably put it in the first, when I get